Okay, so this is our last plenary talk of IMPA 50 years, and definitely this is a situation where the saying last but not least definitely is correct, in particular with a person like Professor Chorin, that if we talk about mathematics in Brazil, we think about the 50 years of IMPA. If we talk about mathematics in fluid dynamics, say for the last 30-something years, Professor Chorin's work is definitely plays a major role. In particular, even my students here at the fluid dynamics course, first thing they would think would be the textbook, that one of our textbooks here, Chorin and Marsley, A Mathematical Introduction to Fluid Dynamics. So it's really a great pleasure to have Professor Chorin here for the first time in Brazil, first time at IMPA. And the title of the talk is Optimal Prediction for Problems with Uncertainty.
Thank you very much. It's a really great pleasure to be here. Can you hear me? I'm grateful to be allowed to celebrate 50 years of IMPA. Well, in fact, this is my first connection with IMPA, but I'm hoping this is in advance. So it's a real pleasure. And I hope you'll invite me for the 100th anniversary of IMPA. The problem I'd like to talk about is, I'll write it in the simplest possible form. Suppose we have a set of differential equations. Let me write it in the form d phi dt equals to r of phi, where phi of 0 equals to x, and phi is a large dimensional vector. Phi 1, this is to mean it's a very large dimensional vector. I really mean n to be infinity, but this is too hard to, notations become difficult, and I don't want to get into technical details which are irrelevant to a large extent. And suppose that you don't have enough information to solve this problem. For example, you may not be able to fit the problem on the computer, which has happened very often in practical problems. So many variables you can't fit in the computer, can't solve the whole problem. Or you don't have all the data. Think of weather forecasting. It's both too big to solve, put in the computer, and you cannot fit, you don't have enough data to make a prediction. Or they are maybe uncertain. And all those things can happen, and in fact, they're all reducible to one case, which is the case I consider, in which, in fact, what you have is you have partial data. And it will not do the transformation from this case to the other case. And in fact, the fact that it says ODEs is also not essential. You can do the same thing for PDEs, for partial differential equations, but the notations get worse. So what we'd like to do is we'd like to find a sub-vector of this one. Let me call this, put here phi m, where m is less than n. And let me introduce one more notation. Let me write the solution of this problem as phi of t and x. And I'd like to put here the initial data as a parameter in the solution, and that's going to be very useful. You can think of that as being Lagrange variables and Eulerian variables if you think of fluids. And I'd like to call this phi roof. And what I'd like to do is find some equation which says d phi roof of the dt, small subset variable, equals to something. The question is, what's the something? With the initial data phi of 0 equals to x roof, where x roof, x is an n-dimensional vector, but I only have the first n pieces. And the question is, what can you do? There are lots of simple situations in which something can be said without the heavy machinery I'm going to introduce. For linear problems, which are not easy, but one can do things in simpler ways than what I'm going to do here. So let me consider mostly nonlinear problems. And also there are problems in which there are other simplifying features to which I'll come back when I introduce the major machinery. So it's the question is, so I'm going to try to produce a heavy machinery. Well, I'm going to do two things. I'm going to first give you a simple machinery for reducing the dimension of the system, which in fact sometimes is useful and requires additional assumptions, and I'll go to the end of that. I'll show you why, in fact, it doesn't work, which is very revealing. And then I'll write down the heavy machinery, which in fact is exact, but then you get problems which are computation, which are very difficult. And then I'll start explaining how one can take the large system of complicated system of equations and simplify it into something which you can handle. And I'll do that on the simplified version, from the first theory, simply because otherwise it takes several hours, and I don't think I have it. Okay? My main tool is going to be conditional expectations. So this is where everybody I lose my audience typically as a matter of course. because people who compute, or people who not necessarily probability, don't necessarily know about conditional expectations and don't like them. People who know about conditional expectations with probability will view my introduction as much too trivial. So let me just give you the simplest possible definition. This is the major tool in all these kind of things. Suppose you have two groups of variables, let's say. I call them x roof and x tilde, the remaining variables. Okay, so x roof is the typical things I know. And you know the joint probability density function. So this is the probability f of x roof and x tilde. Why do we introduce probability? Well, if I take a large system of equations and I want to look at a subset, I have to know something about the others. If I know nothing at all, the problem cannot even be approached. Suppose I give you, I want 10,000 numbers, I give you the first 100 and I ask you to guess the others. There's no way. So something has to be known. And joint probability density functions for all the variables, the ones you can compute, the others which you can't compute, are typically available. Certainly physics problems, from statistical mechanics, from statistical considerations, which are very general in nature, and it's quite reasonable to assume that that's what's known. And therefore, I'm going to try to figure out, so the conditional expectation, suppose that G is a function of variable of x roof and x tilde, the conditional expectation of G of x roof and x tilde given x roof is simply, okay, I'm assuming that somebody has given me x roof, so I can be only on this line. On this line, x roof is known, x tilde is changing, and I'm averaging this function here on this line, which has this intersection with the original f. So this is simply the integral of G of x roof, x tilde, f of x, this is both variables, x roof and x tilde, dx tilde, divided by the integral of f of x dx tilde. This division is necessary to make the probabilities add up to 1. So that the average of the function which is equal to 1 is equal to 1. Okay, so this is the conditional expectation. And there is a basic theorem which tells you that this is a function of x tilde alone. This is a function of x tilde which best approximates this function in the mean square sense. So you have an inequality which tells you that the expected value of g of x minus the expected value of g of x given x roof, the whole thing squared, is less than the expected value of g of x minus any other function of x tilde squared for any function h of x tilde. So if you think of a space of functions, L2, where even the product of u and v is the integral of u of x, v of x, f of x dx. Okay, this is L2. You look at the subset here of functions, let's say h of x tilde alone. This tells you your function g here, it's closest approximation among function of x tilde alone is this conditional expectation of g given x tilde. And that tells you in particular that this difference here is orthogonal to everything in here. And that's a projection. This is a projection. Okay, so this is going to be my main technical tool. I'm going to be calculating conditional expectations. If indeed you have a problem like this, what you're looking for, if you're trying to calculate phi roof, which is you could try to calculate phi roof, the few variables at a later time, what you're looking for is the expected value of phi roof of all the variables, x and t, given x roof. This is the best you can do if you're solving a partial problem. Okay, so this our goal is to calculate this. Calculate this. Okay? And of course, there's an obvious algorithm for doing this. What you do is you pick the variables you know, take x roof, fill all the other variables from the probability density function, sample all the other variables, solve the big problem, do it over and over again for all values of x tilde, of all the variables which you don't have, and average. Which means you're taking a problem that you can't solve once, and then replace it by a problem of solving the same problem many times and averaging. Okay, so the problem is to find some way of calculating this object here while doing less work than solving this big problem once. Okay, and I'll show you that in fact it's not in principle infeasible. So this is as far as I've got so far. And now to show you how this works, let me show you a simple assumption. Assume, so that's a simplistic solution in a special case. Oh, before I forget, this work is joint work with a number of people. I guess maybe I should write down the main names are Hald, Kupferman, Levy, and myself. Okay, put myself last. So assume the system is Hamiltonian. Assume this system here is Hamiltonian. So one way of writing that is the d phi I of a dt equals to dh over d phi I plus 1 for I odd, and d phi I over dt equals to minus dh over d phi I minus 1 for I even, where h is a function h of phi 1 up to phi n is the Hamiltonian. Under those conditions, any function which is positive definite integrates to 1 of h is an invariant probability density for this problem. And I'd like to look at this one. This object here, e to the power minus h, normalized. Z is the integral of e to the power minus h dx. This object is a probability density, which is invariant on the flow. Everybody knows that. We can commute the evolution in time and the sampling to get the same thing. It doesn't mean the solutions in each individually invariant. It means that they remain, if you look at the set, the number of solutions in that set is always the same. This simplifies the problem greatly. So let me do the following thing. Let me take this system here. Assume that the variables I want to keep are the first n. Why not? It means I can order the variables any order I want. The question which variables we really want to compute is a separate issue to which I'll get. Let me assume the variables I want to compute are the first n. So I write the first m equations, and I get d phi I over dt equals to r of phi for I less than m. I can write that if you wish, d phi roof over dt, phi roof is small variables, equals to r roof of phi. Well, now we get into a problem, because the arguments of r roof are all the variables, not only the ones we kept. If somehow or other you simplify, the problem gets simplified so that in fact you get only phi roof here, it's an easy problem. You don't need anything else. Okay? So another question, so I'd like to approximate this as well as I can by what I know. And as is often the case in numerics, what you do is you have a problem which you don't know how to solve. What you do is you approximate the equations in the hope that you approximate the solutions too. It's a vain hope. It won't work. Here it will work under some conditions. So the obvious thing to do is to take the object here and approximate as well as we can by something we do know. So approximate this by the expected value of our roof of phi given phi roof. And this is a meaningful object because at each instant in time, the joint probability density function of all the phi's is known. Therefore, the conditional expectation of R of phi is a well-known, is something which you can calculate. How to calculate that I'll come to. But in principle, you can calculate it. I'll give examples. And therefore, I have a reduced system of equations which has as many components as you may wish. In fact, it makes sense to ask that question for a single equation. Suppose you have one piece of data. You may want to ask yourself, given this one piece of data, what's the best I can say about the future? Okay, it may not be much, but it's something. Before I go and tell you what this does, let me point out that this is a hard problem. I'm trying to predict on the basis of the present what will happen in the future. So, for example, if I know the temperature here, let's say in Rio de Janeiro, and temperature in I don't know, 20 miles from here today, I can try to guess what temperature here is in between the two today. But this is equivalent to asking the question, suppose I know the temperature here today, the temperature someplace else today, what's the temperature in between a year from now? I'm trying to take partial data and use them to predict the future. Okay, therefore, the problem is actually difficult, but that's the kind of problem which arise all the time. And and it's quite obvious, and it should be obvious before I do anything else, is that what I'm trying to calculate, which is this object here, the conditional expectation of the reduced system given the partial initial data, should really tend to 0. The predicted value of data today, of information today, decreases in time. If I know it's very hot today in Rio, it's likely to be hot in Rio tomorrow also. There's some effect, some lingering effect. Okay? But if it's hot in Rio today, there's no way I can tell what's going to be in Rio, what temperature is going to be in Rio 10 years from now, except for the average. I mean, the best predictions go with the average for the time of day. And if the Hamiltonian is symmetric anyway, the average is 0. So you expect the solutions of this system reduces the equation to go down in time. Problem is that actually don't right. Before I show you what's wrong with this, let me show you 2 examples. One successful, misleadingly successful, and one which shows what the problems are. And that will motivate a much more complicated construction. My example 1 is a Schrödinger equation. It's a partial differential equation. I ut equals minus uxx plus q cubed plus p cubed, and where u is equal to q plus ip. It's not the usual Schrödinger equation. It's not u squared times u, alpha squared value times u, which is the usual integrable Schrödinger equation. And the reason I picked a different one is simply pedagogical. So I don't have to answer what happens if you have many integrals of motion, which in fact I can discuss, but it's another lecture. It's a long story. So this in fact is not an integrable system. This is a Hamiltonian system. The Hamiltonian is the integral from 0 to pi, I'm assuming that I'm working on from 0 to pi with periodic boundary conditions, of ux squared, absolute value, plus q4 over 4 plus p4 over 4. I may be mistaken, there may be an I somewhere here, dx. Okay, and the measure, which is invariant, e to the power minus h normalized. Before we go any further, please notice that this Hamiltonian, if you take this probability density, which gives to each bunch of functions, each cylinder set of functions a probability, that this probability in fact lives on something which looks very much like Brownian motions in space. The easiest way to look at this is take this, forget about this for a moment, take the Fourier transform of that, you get something which looks like sum of k squared, uk squared Fourier transform. That means that you have a collection of, and the e to the power minus a sum is a product of the Gaussian. So what you have here is a system with independent Gaussian Fourier components, each one of which is variance 1 over k squared. If you differentiate that such as series once, you get something which doesn't exist, which is unbounded every time. And you get, in fact, the Wiener representation of Brownian motion. So those are not smooth solutions. Those are, in fact, solutions which are nowhere smooth. The question of how to define them is a good question, which I'm going to answer in a moment by writing down a definition. And this is actually one of the great technical difficulties in all these programs of prediction, that when you try to apply them to partial differential equations, the typical Gibbsian measures which you get in fact have samples which are not smooth, and that gets people into difficulty. On the other hand, if you're working problems in molecular dynamics or polymer physics, that's in fact very much the right prior distribution. Let me assume, in addition, that what I have initially, somebody gave me, let's say, 2 Fourier components. That's the graph I'm going to show you. 2 Fourier components. So I have 4 numbers initially. All the rest are known to me, but drawn from this distribution, conditioned by the 2 pieces of information I have. So I have 2 pieces of information. All the rest are drawn from some Gaussian distribution. I can't tell what they are. And what I'm trying to calculate is this conditional expectation there. So I have 2 ways of doing this. One of them is simply write write down the equation for the first two Fourier components, take the conditional expectation with respect to the piece of information which I have, gives me a system of two complex ordinary differential equations, which I can solve in time. The other way I have of solving the problem is the thing which I showed you is stupid, but of course in this case that's easy enough so I can do it. I can take those two pieces of data, complete them by sampling the distribution over and over. So each time I sample the initial distribution, I can solve the equation in time. I have many solutions, I can average them, and hopefully what I get is the same. Okay, so this is an example in which things can be analyzed. And there are many simplifying features here which make this machinery work. So I'd like to show you this. But I'd like to show you, okay, so the first thing which I'd like to show you is what the solution looks like. It's a misleading success. Okay, the problem is, okay, I hope I don't move anything further. Okay, so, there are four possibilities. So this is the one on top is the enlargement of the one on the bottom. The continuous curves are what you get by solving two complex ODs in time. The points are what you get by doing the Monte Carlo many, many times. The solving of the ODs in time takes under a second on the machine. The 10,000 sampling of the Schrödinger equation solution in time takes a couple of days. The two are very close. In fact, if you look in detail, any error that comes from the sampling. So the exact solution is less accurate than the approximate solution I just brought on the board. Looks like a success. I have another example, which I'm going to show you, explain in a moment, which is an example which has been designed to make things work as badly as possible. There are only four possibilities, right? So we'll eventually get there. Right. 8? No, because I don't allow rotations in the. I don't allow rotation like this. 3, 4. Okay, so what you have here is you have a solid curve, which is the truth. It's real average, real conditional expectation. Decays in time, as it should. Okay, I'll explain what the problem is. The one dotted curve is the Galerkin approximation, which simply throw away anything you don't know. The one dotted curve, which starts with being okay, is this algorithm here. And there's another curve which is very close to the truth, which is actually what I'm going to do, done by what I'm going to show you next. And there's a small discrepancy which has to do with lack of ergodicity in the problem. I'll come to that too. Okay, so this is a counterexample. A counterexample which I'll explain, it's been designed to make things look as bad as possible. Okay, so. Only problem is to find here how to do it. That's it. Okay, so my second example is an example which is not helped by any of the accidental features which made this work. This consists of the following thing. The Hamiltonian is h equals 1/2 phi 1 squared plus phi 3 squared plus phi 2 squared plus phi 4 squared plus phi 2 squared phi 4 squared. If you think of that, it's two linear oscillators with a nonlinear coupling, which assume that I have phi 1, 0, phi 1 of 0, and phi 2 of 0. So I know the initial data for one of them. The other one does something at random. And what happens here is the two oscillators have the same frequencies and the same masses. That's the worst possible case for this kind of thing, because the thing which really simplifies calculations, makes it easier, is separation of scale. If you have variables you keep correspond to slow variables of a large physical scale, the kind of variables that you omit correspond to something very fast with very small physical scale. There are lots of reasons to assume, in fact, you can prove that this approximation here, which is on the board somewhere here, is in fact asymptotically correct as the ratio of the fast to the small tends to infinity, whatever the appropriate thing is. And this is just exactly the opposite situation. Here, the equation which I get, the Hamiltonian equations are d phi 1 over dt equals to phi 2 plus phi 2 phi 4 squared, and d phi 2 over dt equals to minus phi 1. That's, I think, correct. Or maybe the minus signs here and here. It doesn't matter very much. And this will be approximated by the expected value of phi 2 plus phi 2 phi 4 squared. Phi 2 given phi 1 and phi 2. Phi 2 given phi 2 is phi 2. So we have to calculate an integral phi 4 squared given phi 1 and phi 2. That's a ratio of Gaussian integrals which you can evaluate. And you get a system of equations which looks like this is replaced here by 1 plus phi 2 squared. Okay, so it's this calculation does something, but what it does is not transparent. So we'll need something better. Okay, so in this situation, because the algorithm failed, and the reason it failed is because something has not been taken into account properly. So now I'm going to try to explain, and I'm not sure that it's going much more sure than I thought, what one should do to get this system. What is the truth? Can I write an equation for this which is completely correct? And the answer is yes. The thing which is interesting is that this machinery which I'm going to introduce you, in fact, comes from physics. It's a version, correct version, of what's known as the Moritz-Zwanzig formalism of irreversible statistical mechanics. I think the thing which we did with it is we proved we did it right. Okay, so this is what I'd like to do. Let me now take this problem and rewrite it. To be able to work with it, I have to be able to transform it into something on which I can do perturbation theory correctly, and in fact, in this case, exactly. So I'm going to take this system of equations here and replace it by linear system. I don't mean linearize it. Any system of equations, however complicated, can be represented as a linear system if, is the problem?
No. Yes.
Okay. Any system of equation can be written as a linear system if you're willing to add to it many additional variables. So that's what I'm going to do. So I'm going to introduce the Liouville operator, which is equal to the sum of Rj of x of phi, or Rj of x, sorry, d over dxi. So I've taken here the right-hand sides here, replaced it by phi by x's, put here right differentiation operators, and look at the equation ut equals to L acting on u, which is a partial differential equation which is linear. Right? It has non-constant coefficient, but it's linear, with the initial condition u of x and 0 equals to g of x. A calculation which I will not do, but it's simply the correspondence between linear partial differential equations and the characteristics, tells me the solution of this problem here is u of x and t equals to g of phi of x and t. You can use it using a chain rule and some additional identities. It's not absolutely trivial, but that's the exact statement. If I can solve this equation, I can obviously solve this equation. All I have to do is plug it in here, the equation. On the other hand, if I can solve this equation here with g of x, the initial data, equals to xj, the corresponding solution is phi j of x and t. Exactly the solution of this problem. Okay, so I can perfectly well, if I can solve this equation for any initial data, in particular I can solve this equation, and this equation is linear. Once I've done that, I can write a symbolic notation. I can write here u is equal to t equal to TL acting on G. L is the generator of a semigroup. I don't need to define properly because any identity which I'm going to use, I can prove by elementary means. So I don't have to make sure that the L exists, in fact, but that this object is well defined, but in fact one can prove it is. And then this identity here simply tells you that e to the power TL acting on G is equal to G times e to the power TL acting on X, this of X. Okay? And one can easily show that L e to the power TL equals to e to the power TL times L. It's obvious for matrices, but not matrices, but I can need a change of variable formula where I can do that. Then this equation here becomes d over dt of e to the power TL acting on xj That's all I care about, right? For j less than n. It's not the only thing which I can use, but the only thing which I care about is the case in which it gives you the original solution, is equal to L e to the power TL acting on xj, which is equal to e to the power TL times L acting on xj, which is equal to, sorry about this, e to the power TL times P L xj plus e to the power TL Q L xj, where P is the operator, the conditional expectation which takes from L2 to L2 roof, the thing which was under the blackboard here. So I've taken this equation, added the identity, Q is equal to I minus L, and I wrote here simply, I can put identity anywhere I want. If you look at this object here, this is roughly what we had here on the board. And first of all, here I no longer need the system to be Hamiltonian, and I don't have to have an invariant measure. All I need is the initial measure, if you look at it carefully. If you look at this operation here, Lxj is simply Rj from the definition of L. PL of xj is the conditional expectation of Rj given X roof by construction. And e to the power TL is the propagation of that in time. So if you look at what this term represents, it's up to some technical details, which I don't want to get into because it's not quite relevant, is exactly what I have here. Okay? The problem comes from the fact that here you have invariant measures, so this is well defined. Here you don't necessarily have an invariant measure, so you have to work a bit harder to give a meaning to all those quantities. The expected conditional expectations are here not with respect to the invariant measure, but with respect to the initial measure, which requires a bit more writing. But basically, this is what we had before. This has been omitted, and this should not be omitted. This here says that this object here, if you apply P to it, of course, it's going to be 0. So the conditional expectation of this object is, of course, 0. But there's a transport here in time, which goes with the full operator. There's no reason to believe the things you omitted at time t equals to 0 will not have impact on the thing which you're going to develop later. So the omission of this term here is what made this is the error term in this approximation, and you can easily see that for the problem here, this term is actually grows catastrophically. It's of order 1 very fast. So the next thing which you do is I have to take this object here and write it in some way which I can work with. And this gives rise to a very nice formula. Okay. So here, there's no approximation whatsoever. This is true. Okay. I've not arbitrarily taken some object and replaced it by something close by. Now let me go over some steps. You can simply write, here's an identity, e to the power TL equals to e to the power QL times t plus the integral from 0 to t of e to the power t minus s times L times PL times e to the power s QL ds. Looks like a very obscure formula. It's known, it has lots of names in the literature. What it is the Duhamel's principle. But you can take a partial, any kind of differential equation, add a perturbation and see that the effect of the perturbation, if L is equal to QL plus PL, PL is the perturbation, and this is the effect of perturbation on some operator. So it's not a big deal. Take this formula here, replace it here, and what you're going to get is d over dt e to the power TL, sorry about the writing, xj, equals to e to the power TL PL xj. This we know what to do with. Okay, that's an easy object. Plus e to the power t QL acting on QL xj. That's because of this object here. Plus integral from 0 to t of e to the power t minus s times L times PL times e to the power SQL times QL xj ds. Okay? And one can easily show that the P acting. We don't care for this. What we would like to find is the conditional expectation. This is phi j. Okay, that's the solution at a later time of one of the components we're looking for. And what we'd like to find is conditional expectation. So what we're going to do is multiply this by P, multiply this by P, okay? And multiply this by P, and multiply this by P, and this one can easily show is actually 0. And what you have to do is evaluate this term to get a completely error-free approximation. It's not approximation. You get a new representation of the problem in which on the left-hand side you have only the things you like to compute. On the right-hand side you have some objects which you can conceivably compute too. Nothing has been greatly simplified in here. It's exactly, the problem here is exactly the same as the problem there. It's simply that what I've done is I've written on the left-hand side the things which I want to compute in terms of things which I don't know how to compute. Okay? This is actually known as fluctuation dissipation theorem as a generalized algebraic equation, as a fluctuation dissipation theorem, lots of names here. The difficulty here is calculating this object. Even though it vanishes here, it appears in the integral. You have here this object e to the power SQL. E to the power SQL is the solution of the problem d over dt of, suppose u equals to e to the power SQL acting on QL xj. That's the same thing as solving the d of dt equals to q times L times u, which is equal to p times L times u plus q times, sorry, u has minus p times L times u, with initial data u of x and 0 equals to q L xj, which you can translate this as rj, this 1 minus rj. And this problem is actually difficult to solve. It involves all the things you don't know. QL projects you on the space of variables you don't have. So in principle, what you have here is the statement that to calculate the things you want to know, you have to calculate the things, all the things you don't want to know, and what has been gained. Before I go any further, so this is the question. Another question is what to do with it, and let me start to give you an answer. The first thing which you may want to notice is that what this looks like is a memory term. It looks like the solution time t depends not only what happens instantaneously, but on the past also. So you've taken a Markovian problem for the variables, for the whole set of variables, and transformed it into a non-Markovian problem for part of their variables. This is unavoidable. Okay, it's a general theorem that you have to have memory. If you want to have intuition, suppose I want to look at billiard balls on a table, about 20 of them, and want to follow 3 of them. The first one may collide with 17th at time t equals to 0. The 17th may actually collide with the rest of the board and come back and haunt you after some time. So you have to remember everything which happened to the variables which you omitted. That's life. What the 3 of us, the names here were Chorin, Hall, and Kupferman, was we constructed an algorithm for evaluating P acting on this, which involves only the variables which you want to keep. It's a long construction, and I don't want to explain it. I don't want to explain it. I can give you a reference to it, because it's actually impractical. Even though it uses only the variables that you want to keep, you can transform this object into an integral equation working on in L to roof, and it's an integral equation which you can solve, and it's well conditioned, and the rest of the stuff is complicated. And the problems are that it requires an expansion in an orthonormal basis whose convergence property is actually unpleasant. They converge, but converge slowly, and the convergence cannot be improved. So even though in principle you can do that, it's a practical problem. In principle, you can actually work only with the variables phi roof. In practice, you maybe cannot. So there's an alternative. And let me try to start expanding the alternative. Okay. So this is the truth. The problem with the truth is that it's painful. You shall know the truth, and it will make you suffer. And the question is, how do you make the painful truth into a simpler truth, which is actually computationally useful? Okay, so here comes the simplification of the facts. Among other things, you can show out of this formula that if you have a big ratio, fast scales and small scales, and it's well separated, then this term is negligible. Or there's other conditions you can replace by Brownian motion and all sorts of things, which are very simple and well known. You can derive out of that standard machineries, which are quite familiar, I guess, to everybody who works in some kind of prediction. Let me start with a theorem which is due to Hall. Start with Hamiltonian system. d phi over dt equals to r of phi. approximated by a reduced system, d phi roof over dt equals to the expected value of r roof of phi given phi roof, assuming there's an invalid measure again. I'm returning back to the simpler situation which I dealt with initially because it's simpler. Then the Halt's theorem says, this is also Hamiltonian. Okay? There's a very simple, nice formula if you're willing to use a proof using a Nicodim derivative, just one line, but it's still one line. You look at the terms here look like I've erased the equations. If you look at something like d of the dx1 of h, the expected value of this given x roof, this is x1. This is a typical right-hand side. If the h is Hamiltonian, the typical right-hand side of the equation, the derivative of the Hamiltonian, this is by definition the integral of d of a dx1 of h of x e to the power minus h of x dx tilde divided by the integral of e to the power minus h of x dx tilde, the definition of conditional expectation as we had it before. And this is obviously equal to minus d over dx1 of log of the integral of e to the power minus h dx tilde. Okay, so this, and therefore the new Hamiltonian new reduced is equal to minus the log of the integral of the e to the power minus h times the old Hamiltonian integrated of all the variables which you don't want to keep. Okay, so this is what I'm going to, this is my key tool. This proves, by the way, that the approximation which you got here cannot possibly be uniform in time. Take a simple example in which the average of any function, the h has some symmetries, the value of all the variables should decay, but if there is an invariant quantity which is not linear in the variables, and this one is not, you cannot decay. So this, in fact, contains the proof that this approximation cannot be uniform in time. That those nice pictures I showed you can maybe run for a long time and be nice, but eventually it will be disastrous. Now what I'd like to do is I'd like to show that this construction here is identical to a renormalization group transformation. And I'm going to show it's not renormalization groups are not well-defined objects. I'm going to find one which is perfectly well-defined, and I'm going to show that it's exactly the same. That up to some change of variables, this, in fact, the reduction from here to here is a renormalization group calculation. And once I have the renormalization group operation, there's a whole variety of machinery which has been developed in physics, which allows you to calculate this kind of object and this kind of object relative ease, with great intellectual difficulty, but actually small computational difficulty. I don't know to what extent. How long can I talk? I thought I'd get here a bit faster. So the claim is the following. Let me just write it out. Let me take a simple situation. Suppose I have a line, and on the line I have a collection of variables. x1, x2, x3, x4, up to xn. And suppose I'd like to get rid of this one, this one, this one, and this one. And the big difference between what I'm doing here, and I'd like to keep this one, this one, this one, and this one. So the difference between what I did before and now is before I collected all the variables I want to keep at the beginning of the vector. Now I sort of change the order so that I keep one variable, omit one variable, keep one variable, omit one variable. And now what I'd like to do is I'd like to find, and this is the probability density on this collection of variables e to the power minus h, normalized. And now I'd like to find, let me call it h1 of x1, and this is the vector x1. Then I'd like to find a variable, a Hamiltonian h2, such that e to the power minus h2 of x2 contains only this variable, this variable, this variable, and this variable, that the this probability density properly normalized has the same marginals as this probability density here, which means I'd like to keep the probability density of the variables I keep the same as the probability density of the variables I've omitted. And if you look at the calculation, which I'm not going to, if you look at the relationship between those two here, you find that H2 must be equal to e to the power minus H2 equals to e to the power must equal to e to the power minus H1 dx tilde, which means that H2 is equal to minus log the integral of e to the power minus H1 times dx tilde. And if you notice that this relationship here and that relationship are exactly the same. So one step in the realization group transformation is exactly the same thing as a reduction in number of variables here by a factor of 2. And there is a very good machinery, both perturbative and numerical, for doing such reductions. And I will not, if you want to see the details, they're on my website, and it's a fairly long calculation. And the next statement is that once you go from this approximation to this approximation with this nasty term added, use the construction which you used before to reduce it all to the space of variables spanned by X roof. Then you have another version of the normalization group transformation, which allows you to calculate those variables here, including this term. And that, in principle, solves your problem. It doesn't solve all the problems because it's still a hard thing to do, but it may well be much more practical than other ways of reducing systems. I think I'll stop here.
Questions?
What's the connection with reversible thermodynamics?
The problem, suppose one can view the problem, suppose we have suppose the probability density is the prior distribution initially is e to the power minus h, which is the Gibbs distribution. You can view the situation in which you know the first few variables, but don't know the others, and the sample from the equilibrium distribution conditioned by what you know, as a system. Look at the system in which you've taken equilibrium, perturbed it by taking some variables and giving them fixed values. You're no longer then in equilibrium, and you let it go, and the system will decay towards thermal equilibrium. So this is an exact equivalence of what I've shown you on the board. I know some variables, but because of nonlinear interaction, the system will decay towards its equilibrium, in which, in fact, it's forgotten the preparation of the system away from equilibrium, and therefore that's one way of showing that the predictive value of present knowledge in nonlinear systems, in fact, shrinks to 0. And it's the same problem, and the thing which has been translated here is machinery with concepts of physical mechanics. We've done some other things, some things. In particular, we've fixed it up, removed mistakes, we've proved that the things are correct, we've proved existence, uniqueness, all the stuff that's something which mathematicians do, and we have produced at least one algorithm which works, which I think is an improvement.
Questions? Okay, well, thank you very much.
Thank you.
That example that you showed here, that you called the memory one, is this the Schrödinger equation model?
Which one?
This one that fitted very well, right? The truth with the memory. Or in this one that you showed truth and memory, that you had a perfect fit with no